Hello everyone. So in this video I'm going to discuss some problems from INMO 2023. So the exam was held yesterday, and so I'm going to discuss problem 1, 2 and 5 in this video. So let's first go to the first problem. So the problem is saying that you have a finite set of positive integers, and when you are when you're doing x cross s, so then you're basically getting 2023 ordered pairs xy precisely such that xy is a perfect square. Okay, so then you have to prove that one can find at least 4 distinct elements in the set S, such that if you do pairwise product, so then they won't be perfect squares. Okay, so an example also has been given, like what they mean by S cross S, and what they mean also by xy is a perfect square. So S is equals to the set is given to be 1 to 4, and as usual you can see that when each element is getting multiplied with itself, it's forming a square obviously, and if two squares are also multiplied, it forms a square. And also sometimes, like 2 cross 2, two non perfect squares also getting multiplied to get a square. But yes, now the thing is that how do we get these at least 4 elements which are not a perfect, so their pairwise product won't be a perfect square. So to attack this problem, first of all you can think in the direction of prime factorization, and also you can think like what's the speciality of this 2023. Okay, so I also tried first in that way, but again it was a dead end for me. But there is another very nice and elegant solution where I'll be using relation on the set S. So let's proceed. So what I'll be doing is that I'll be defining a relation on the set S. So I'll be defining a relation on the elements of the set S. Okay. So how I'll define is that x is related to y if and only if xy is a perfect square. Okay, so if xy is a perfect square, x and y are related, and x and y are related, that means that xy is a perfect square. Okay, so this relation I'm claiming that it's an equivalence relation. So what does it mean is that this relation is transitive, symmetric and reflexive. Okay, so let's first go with this very simple one, reflexive. That is just as we talked about, like x is related to itself. Why? Because x is a the set S is defined that you are having positive integers in that. So x squared is a perfect square. Now what about symmetric? That is also very simple. That is xy is some perfect square where k belongs to z. Then also it implies that yx is a perfect square. Okay, there is nothing in that. And the main part is that the transitive relation. So what about the transitivity? So suppose this x is related to y and y is related to z. Does that imply that x and z are related? So let's see. So if x y is equal to some k1 square, and y z is equal to some k2 square, where k1 and k2 belongs to z. So then what happens is that so if we need to show that x and z are related, so we have to show that z is a perfect square, right? So let's multiply both of these. So it implies here that x z y squared is k1 k2 whole square. So let's boil it down to xz, which is coming out to be k1 k2 divided by y whole square. Okay, now the question arises is that is it a perfect square? Is it a square of an integer? Okay, so the first thing is that note that whatever it is, the inside this part is a rational number, okay? And also the whole thing needs to be an integer because the left hand side is an integer, right? So now the square of a rational number is an integer, okay? So that also means that that rational number is an integer. And if you want to prove, I leave it to you, so it's not very hard to see that. And yes, so from there we can conclude that x and z are related, okay? So this implies x is related to z. So now what we are having is that we are having an equivalence relation on the set S, okay? So now if we are having an equivalence relation on the set S, how does it help us? So what happens is that, suppose this is the set S, okay? So there are the elements in this set S, and now what I'll do is this set is also finite, it's given. So I'll arbitrarily pick up an element X, and I'll see that what are the elements which are related to that set element X, okay? And I'll just form a partition of this set S as the elements which are all related, all the elements of the set S which are related to that element X. Now since this relation as we talked about, it's transitive, so if X is related to some other element and also X is related to suppose another element, so those two elements will also be related, okay? So yeah, since the relation is an equivalence relation, okay? So from there what we can say is that all the elements will be related. And suppose if I start with the set X, the element X, and I find no other elements which are related to X, so then okay, fine, so that equivalence class will just consist of that element, singleton element X, okay? So suppose yeah, this equivalence class is starting with is having A1 elements, okay? Then again and also moreover, like once I partition this part, so the rest of the elements in the set S, none of them will be related to this any of the element in this partition, because then that element would have been in this partition, okay, if it's related. So that's why none of the rest of the elements are related. And so again I'll repeat the same process, that I'll just take one element from the remaining set, and again I'll just form another partition, suppose there are A2, and like this if I just continue on, and so after some time I'll be able to exhaust the set S, because the set S is having finitely many elements, okay? So let there be k such equivalence classes, and the ith equivalence class is having ai number of elements, okay? So now yes, one more thing is that if I pick up an element from one equivalence class and another element from another equivalence class, so the product won't be a perfect square, because they are not related. If they were related, then because if it would form a perfect square, then they are related. So if they are related, then they would have been in the same equivalence class. So yeah, so that means if I pick up two elements from two different classes, I won't be so the product won't be ever becoming a perfect square. So from there what we can say is that the problem is basically asking me to prove that there will be at least 4 such equivalence classes, because if I pick up one element from each of those equivalence classes, then any two you take and take the products, never going to be a perfect square. So now what about this 2023? So that's something we haven't still used. So now this set first thing, that this first equivalence class, so since there are A1 elements, so how many perfect squares are they going to make? So they are going to make A1 square perfect squares, because every element is related to every element in that equivalence class, okay? And so every element would just get multiplied with every other element, and even by with itself, and will form A1 square number of perfect squares, everyone getting multiplied with everyone, even themselves, okay, and forming perfect squares, because they are all related even to itself, okay? So similarly A2 squares, perfect squares coming from the second equivalence class, and so on and so forth, AK square, and since we know that the total is 2023 perfect squares that is getting formed. Now the question is, how do we so we basically have to show k is greater than or equals to 4. So how do we show that? So here what happens is that if we take this equation under modulo 8, so you see that 2023 is congruent to 7 modulo 8. So and also we know that if we divide any perfect square by 8, so the remainders are 0, 1 and 4. The possible remainders are 0, 1 and 4. So a1 square, even if you have three such perfect squares, a1 square, a2 square, a3 square, so that can't be congruent to 7 modulo 8. Why? Because a combination of 0, 1 and 4 won't give you a sum where you will that will be congruent to 7 modulo 8. But yes, starting from 4 onwards, you can have like 1 will be 4 and there will be 3 ones, and so you can have 7. So that proves that k will be greater than equals to 4. And so since we are having 4 equivalence classes, just pick one element from each of those equivalence classes, and those 4 elements are our required elements. So from each of those equivalence classes, you can pick up any one of them arbitrarily. Okay, doesn't matter which one you pick up. So, and yes, so yeah, those 4 elements those 4 elements are not unique. Okay, but yes, according to the equivalence class, so you can say the uniqueness, but let's leave it apart. We have got our 4 elements. So this 2023 is nothing special, as you can very well see that if we have any number which is like congruent to 7 modulo 8 would have worked, like even the year 2015 would have worked, and also the coming like let's add 8 with 2023, so even 2031 would work. So yeah, it doesn't matter, like 2020, so 2023 is just nothing but congruent to 7 modulo 8. Okay, so yes, that's all about the first question. Okay, so now yeah, let's go to the second one. Okay, problem 2 says that you have a polynomial where so you not only have one polynomial, basically you have several polynomials here. Okay, so basically 101 polynomials. Okay, so these a0 till a100, these coefficients are positive reals, and you're considering this polynomial for every k, and k can be any one of these 0, 1 till 100. Okay, so the polynomial is a100 plus k x to the power 100 and 100 a 99 plus k x to the power 99, and whatever, you can just see the polynomial. Okay, so notice one thing about this polynomial is that all the coefficients are fine, but only the second coefficient, there is 100 multiplied with it. So that gives us a hint that there is something, I mean, we should do about that. I mean, we should think about what we can do with that coefficient, because that is a special one. Okay, and so if the indices exceed 101, then you should take them under modulo I mean, if they exceed 100, then you should take them under modulo 101. Okay, so a100 plus I is equals to ai minus 1 for any I in belonging to 1 to 100. Okay, so yeah, that's very that's nothing like something that is just given to like define the coefficients where you have the index which is greater than 100. Okay, because so k is given to be going from 0 to 100. Okay, so now what we have to show that it is impossible for each of these 101 polynomials has all its roots real. Okay, so all these polynomials, we have to show that all of them can't have all of their roots to be real. So then what we can do? Okay, so let's do one thing. Let's let's take that all these polynomials, all their roots are real. Okay, So I mean we would just proceed with the help of contradiction. Okay, that is the best approach like we usually do in these type of problems. Okay, next what that is, we see that all these coefficients are positive. So if I plug in any positive value of x, this sum is never going to be 0, right? So we get that if roots exist, then they have to be negative real numbers. Okay, for so if the I mean all, so since we are considering, our hypothesis is that all the roots of this polynomial is real, so then those real numbers have to be negative real numbers. Okay, strictly negative real numbers, because even 0 won't work, because ak is also positive. So let's start with our hypothesis. Saying that let's denote these polynomials as pk. Okay, so pkx. So for k going from k can be I mean one of these 0, 1 till 100. Okay, so let all the roots of pk x be reals, okay, where k belongs to 0, 1 till 100. Okay, so now let the roots be since they all have to be negative, so let's take negative alpha 1, negative alpha 2, negative alpha, so it's of degree 100, right? So there will be 100 roots, so negative alpha 100. Okay, where all these alpha i's are strictly greater than 0, and for all I going from 1 to 100. Okay, so these are the 100 roots, and now what we will do is since the alpha i's are positive, so we can do AMGM. So we can perform AMGM inequality. Why are we doing that? Because the idea comes here, that is, this coefficient is basically related to the sum of the roots, right? So the sum of the roots, let's come here. So then sum of alpha i's. Okay, so sum of the roots, you can very well see that this sum of these negative alpha i's is negative 100 a99 plus k divided by a100 plus k. So then the sum of the alpha i's would be so let's first write the, so I going from 1 to 100, and that is greater than equals to product alpha I. So alpha i's are positive. So let's take j here. So j running from 1 to 100 and whole to the power 1 over 100. Okay, and now sum of these negative alpha i's is that, so negative negative cancels out, and we will be having so this is a99 plus k. So even that this 100 and that divided by 100 would also cancel out. So a99 plus k divided by a100 plus k. The final thing, a99 plus k divided by a100 plus k. Okay. So and let's take to the power 100 on both the sides. So whole to the power 100 is greater than equals to product. So the product would be here ak divided by a100 plus k. So ak divided by a100 plus k. Okay. So now k belongs to 0, 1 till 100. Now there is one interesting thing, that is for k equals 0, what do you get? A99 divided by A100 whole to the power 100 is greater than equals to A0 divided by A100. Then for k equals 1, again you get just check, A100 divided by A101. So A101 is basically A0. Okay, so I'm not you can reduce them. Okay, so just get the point what I'm trying to do. Okay, you can reduce them under the index under modulo 101. So that's not a problem. So we are taking k equals 1, so A1 divided by A101. Okay, and so on and so forth till k equals 100. Okay, so when k equals 100, so we would be getting here 199 A199 divided by A100 plus 100, which is A200 whole to the power 100 is greater than equals to we are taking k equals 100, so A100 by A200. Now notice one thing, if I just take the product of all these 101 inequalities, so look at the right hand side. The right hand side, you on the numerator you are having A0, A1 till A100, all the products of all these coefficients. Okay, and below also you are having A100. Okay, and then this A0, A101 would just boil down to A0, and then you would get next A1, A2 till A200 is nothing but A99. So A0, A1, A2 till A99, and also you got A100 here. So even in the denominator you are getting the total whatever you are getting in the numerator. So things would cancel out and you would be getting 1. Okay, so the right hand side is 1, so greater than equals to 1. And now look at the left hand side. So the left hand side, you can very well see that things would just cancel out here, like this A100 with cancel out with this, and so on and so forth. And so what will survive or remain at the end is A199 and A200 here. Okay, so these two would survive. So A99 divided by A200 whole to the power 100. Okay, but what you see is that again under modulo 101, A200 is nothing but A99. So again these two cancels out and we get 1 is greater than equals to 1. Okay, so now we see that basically it's the equality is holding. So that implies that here we would be having equality for all k. So let's replace this inequality now by equality. So what we are actually having here, okay, so if you see that if we look at this as AI, so it's AI divided by AI plus 1. So let me write it down. So what we are basically getting is AI divided by AI plus 1 whole to the power 100 is equal to, this side I can write that as AI plus 2. Okay, because if A99 plus k is AI, okay, so if I add 2 with it, I am going to get k, because 101 is going to be 0 under modulo 101. So AI plus 2 divided by AI plus 1. AI plus 2 divided by AI plus 1. Okay, so this is what I am basically getting. Okay, now so I'm getting a very nice relation about these coefficients. So from here I have to deduce something about the coefficient. So now notice one thing, that is, suppose from here what we can say is that if AI is greater than AI plus 1, then this the left hand side would be greater than 1, and so the right hand side would also have to be greater than 1, and so for that ai plus 2 has to be greater than ai plus 1. Okay, and if the opposite thing happens, that is if ai is strictly lesser than ai plus 1, then again since the ratio has to be less than 1, so ai plus 1 has to be greater than ai plus 2. Okay, so this is like so what I'm trying to finally conclude is that all the coefficients would be equal. Okay, so let's start with like this, that is none of the coefficients are equal. Okay, so none of the coefficients so I'm going like this, that is none of the coefficients are equal, and so then if ith coefficient is greater than the next one, then that next coefficient has to be lesser than the next coefficient. Okay, so now this is what I notice here, okay, from this relation that I am getting about the coefficient. So let's start with the very first coefficients, that is a0 and a1. So if a0 is greater than a1, so first I'll try to prove that a0 and a1 are equal. Okay, and similarly if I can do that, I'll just then similarly proceed by induction on I, and I can prove that like a1 will be equal to a2, and similarly like I can proceed there, and I can prove that ai is equal to ai plus 1. Okay, so a0 if it's greater than a1, then what do we get? We get that a0 is greater than a1, and again a1 will be lesser than a2, and a2 again would be greater than a3, and a3 would be lesser than a4, and so on and so forth. Okay, this would continue. So what you observe here is that ai is greater than ai plus 1 for all even I, or all for all I even. Okay, and ai is less than so for the odd coefficients, what is happening is that, suppose let's take a3, so a3 is lesser than a4, so ai is less than ai plus 1 for all I odd. Okay, so then what we will have, that if we proceed like this, then we will have that a100 will be greater than 100 is even, so it will be greater than a101, but a101 is actually what? It's a0, but again we have this relation, that is a0 is greater than a1. Okay, and again what we have so yeah, okay, yeah, we are done. So what we are having here is a100 is greater than a0, and a0 is greater than a1. Okay, and that is a contradiction, because basically when you will be having this relation, okay, involving a100, a0 and a1, then you will be so if like a100 is greater than a0, then a0 has to be lesser than a1. Okay, so all the three cannot be like in an increasing in a decreasing order. Okay, three consecutive can't be in decreasing order, because we just proved here, that is if one is greater than the other, then the next one has to be lesser than the next one. So this is what we proved, and so that's why we are having a contradiction. Okay, so a0 cannot be greater than a1. Similarly, just if you just go like a0 is then less than a1, and similarly proceed, so what you will be getting is that this relation would just reverse, that is ai is lesser than ai plus 1 for all I even, and ai is less than, or sorry, greater than ai plus 1. So I'm not discussing this in detail, because it's just similar to the other case, just you have to observe. And so again what will happen is that A100 will be lesser than A101, okay, and A101 is A0, and A0 is lesser than A1, and so all these A100, A0 and A1, they are in an increasing order, so that can't again happen, and again we have a contradiction, and thus we prove that A0 has to be equal to A1, okay. And now I leave the inductive part to you, okay. So similarly we can proceed and induct on I and prove that AI is equal to AI plus 1 for all I. Okay, so that means all the coefficients are equal. Now we have something very, very nice, that is all the coefficients are equal. So if for this polynomial, if all the coefficients are equal, so just take out that coefficient, okay. So if you multiply a polynomial by a constant factor, so the roots do not change, okay. So if you just take that coefficient common and just delete that, so whatever remains, so the roots are still the same, okay. And so let's go there, and so then let f of x, or f of x is equals to let's take that this x to the power 100, x to 100, x to the power 99, x to the power 100 plus 100, x to the power 99, x to the power 98, and so on. So till the last coefficient will be 1, because all the coefficients are equal and I have taken it out. Okay, so now it all boils down to this polynomial, whether it has all real roots or not. So again, just how we proceed, how we have started this problem. So again, the same thing we will do it here, that is again AMGM inequality. So again, so suppose the roots are x1, x2, so let's take negative x1, negative x2, and so on till negative x100, okay. So these are the roots of f of x, and xi's are strictly greater than 0 for all I going from 1 to 100, 1 to 100, okay. And f of xi, negative xi, is equal to 0 for all I going from 1 to 100, okay. So then what, again let's apply the AMGM inequality. So the sum of all the xi's would be what? Would be again so sum of all the negative xi's would be negative 100. So negative negative cancels out, so sum of all these xi's is 100, okay. And since we are summing up 100 real numbers, so average dividing by 100 greater than equals to again whole to the power 100, and the product, so the product is 1, as you can see here, okay. And so what we get here is that again the equality holds for AMGM, and for AMGM the equality would hold when all the terms involved are equal, okay. So that means all these xi's are equal, so it implies that, so here we are getting 1 greater than equals to 1, so equality holds. So then what we get here is that all the xi's are equal, so implies that so xi all xi's are equal for all I. Okay, I'm not writing in very detailed. So just get the point. Let's get to the point. That is, since all the xi's are equal and their sum is negative 100, so that implies that xi is equal to negative 1. Okay, for all I. And so now let's look at what is f of negative 1. So it's saying that negative 1 has to be a root. So f of negative 1, if you look at, just put negative 1. So this part is having 99 elements. So those negative plus 1 minus 1 would cancel out and 1 would be left out. And so this part would sum up to be 1. This will give you 1 and this will give you negative 100. Okay, so you are basically getting negative 98, which is not equals to 0, and so negative 1 is not a root. Okay, and so that's a contradiction. That is that is a contradiction to our hypothesis. That is, all the roots of pk x are all real for k belonging to 0 to 100, and so since our hypothesis is wrong, so we have proved that all the roots of pk cannot be real. And yeah, so that brings us to the end of this problem. Okay, so yes, the next problem that we are going to solve is problem number 5. Okay, coming down to problem number 5, what it says that Euler marks n different points in the Euclidean plane, and for each pairs of marked points, whatever be the distance, so Gauss is writing down the integer, which is the greatest integer part of log d2, and yeah, the d is the distance between the 2 points. Okay, any 2 points. And likewise, Gauss is listing down integers, and so if you just count the distinct integers, the count of it will be at most 2n. Okay, not even at most. It's said that strictly, I mean, Gauss writes down less than 2n. So that means the count will be lesser than or equals to 2n minus 1. Okay, and so the definition of this is given. That is, if I mean, log 2d, the greatest integer part of it is the integer which is greater than equals to 2 to the power. So if the integer is k, it's greater than equals to 2 to the power k and less than 2 to the power k plus 1. Okay, so now suppose if someone is writing down these integers, and so the distances so between any 2 points are marked, so that means there are n choose through distances, right? Because there are n points. Okay, but then how do we show that it's strictly lesser than 2n? So first of all, among these integers, think that I mean, try to work on with just the even integers. Okay, so whenever these even integers Gauss is writing down, okay, so then try to see that I mean, try to see that which points are indicating this distance. Okay, so since we are just concerned with the distinct integers, so what we'll do is, like, we would just take any 2 points which are yeah, which are giving that distance. Okay, so we just marked 2 points which are giving that distance. Any other 2 points which is giving the same distance doesn't matter, because that's a repetition. So we are just concerned with the so okay, so suppose these are the 2 points, and this is one of the even integers, and so on and so forth, like again another 2 integers and whatever. So now try to think. Okay, try to think like this. That is, suppose the n points are there on this plane, and I'm doing this. Now how many edges can I get with these even integers? Okay, so how many such distinct edges can I get with these corresponding to these even integers? Okay. So I'm not again counting for particular even integer. I'm just counting the correspondingly one edge. Okay. So how many such distinct edges can I get? So now, since I have to show that the total count is less than 2n, so or basically I have to show that it's less than 2 or equals to 2n minus 1. So it gives me an idea that the even numbers and the odd numbers. So if I can show that the even numbers, they are somewhat less than uh, 2n, so let's say not 2n, sorry, 2n, we have to show the total thing. So if I can show that it's less than strictly less than n, and also if I can show that the even numbers, they are also, the count of the odd numbers is strictly less than n, and the count of the even numbers, that is also strictly less than n, then I'll be done. That is, the sum of the whole thing is strictly less than 2n. Okay. So now let's work with the even integers, okay, for now. And a similar approach would be done for the odd integers as well. So for every even integer, Gauss is written down. We just take all the distinct even integers, we take it, and we are just marking these edges, okay. And now if you continue on like this, okay, so then we claim that there would be, or basically if I want to show that the number of such edges is strictly less than n, okay, so that means like maybe less than or equals to n minus 1, then there is one thing which is basically helping us, that is, suppose if I have n points on a plane, okay, I know that there could be at max, there could be at max n minus 1 edges of non-cyclic graph. Okay, so of an acyclic graph, I can have n minus 1 edges, okay, given n points. So like if you want to draw, n minus 1 is the max. Okay, so given n points on a plane, I can draw max n minus 1 edges, so that in such a way that I won't form a cycle. Okay, so it's basic graph theory, just go and check it out. So I leave that part to you. Okay, so yeah, it's a very nice result that I can have n minus 1 at most such edges. But for that, again, I have to prove that such edges are not forming a cycle. Okay, so if I can prove that, then I'll be done that the even numbers are lesser than or equals to n minus 1, the count of the even numbers. Okay, because I can have at most n minus 1 edges without having a cycle, without getting involved in a cycle. So on the contrary, let's think that, okay, so let there be some cycle which is forming, and its length is k. Okay, so a k-sided cycle is forming. So and for that cycle, suppose a k-sided cycle is whatever. Okay, so this is not a k-side, but just think like this. That is, so the first side, okay, would have some distance, and for which we got an even number, and for each such side, whatever be the distance d, and we took log 2d, greatest integer part, and we got some even numbers. Okay, and it is having k sides. Fine, and k is strictly less than or less than equals to n. Okay, so then what happens is that now we will be collecting these even numbers. Okay, so corresponding to those edges. So and let's arrange those even numbers in increasing order. So suppose 2L1 is less than 2L2, okay, and is less than 2L3 and so on and so forth, is less than there are k sides, so 2Lk minus 1 less than 2Lk, okay. And yes, so remember one thing, why strictly less than? Because we are taking distinct even integers, right? So our count is involving distinct numbers, correct? And that's why I clearly told you that we are taking those distinct even integers. So these are the distinct even integers, and that's why the relation is strict. So now what's next is that so these 2L1, 2L2, 2L3 and so on. So they might be corresponding to, so suppose this is corresponding to the distance D1, D2, D3, okay. So might not be in that order, but yeah, let's just suppose D1, D2, D3 or whatever you can say. So they are corresponding to some distance, right? So that's what I am denoting. So dk minus 1 and dk. Okay, so now this summation di I going from 1 to k minus 1 is lesser than, is strictly lesser than, because all these di's are strictly lesser than 2 to the power 2 li plus 1. Just use this definition here, okay. So strictly less than 2 to the power 2 L1 plus 1 plus 2 to the power 2 L2 plus 1 plus dot dot 2 to the power 2 Lk minus 1 plus 1, okay. Now notice one thing, that I can't do anything with this summation because L1, L2, Lk minus 1, whatever, I don't know what those are. So they might not be like those LIs might not be consecutive or something. So I don't know the common ratio, and so I can't sum it up, okay. But what I can do is, so the last one is the greatest one. So what I'll do is I'll just take that common. So 2 to the power 2Lk minus 1 plus 1. And now I know one thing, that is the last one, okay, whatever its power is, so that power will be at least the last odd number. So this is an odd integer, so whatever be the power of the previous power of 2, so it will be at least the previous odd number, right, or might be lesser than that, so at least, right. So I'll take 2 square, and then the next one might be at least 2 to the power 4, okay, and so on, and so this infinite series I am adding it up, okay. So this thing is strictly greater than that, no doubt, okay. And so finally what I am getting here is 2 to the power 2Lk minus 1 plus 1, and if I add this up, so I am getting 1 by 1 minus 1 by 2 square, and this is coming out to be 2 to the power 2Lk minus 1 plus 1 times 4 by 3, okay. So one of the two I'll take it here, so 2 to the power 2Lk minus 1 plus 2 and 1, this is 2 by 3. Now 2 by 3 is less than 1, and so this is less than 2 to the power 2Lk minus 1 plus 2. And now notice that this could be the like 2Lk minus 1 plus 2 could be the next even number, but we don't know again Lk and Lk minus 1 the relation. So all we can say is that this is lesser than or equals to 2 to the power 2Lk, okay. And so all you can see is that this thing and this thing is lesser than or equals to dk. Okay, so wherever that side dk is, so that is its length is strictly greater than the sum of the rest of the sum of the rest of the edges of that cycle, right? So suppose if this is dk, then between these 2 points, the shortest distance is like shortest distance between 2 points is a straight line, right? So I mean dk would be the shortest distance, so that means like the sum of the remaining sides, that would have been greater than, strictly greater than dk, but the opposite thing is happening, and so that's giving us that we have a contradiction. So what is the contradiction? That our hypothesis was that we took that let there be a cycle of length k, so that then we are getting a contradiction, and so this implies that no cycle. Okay, and so if there is no cycle, so that means those edges, so we can have at most n minus 1 of them, and so corresponding to them we can have at most n minus 1 even integers. Okay, and so we proved that the even integers count is lesser than or equals to n minus 1. Similarly, you can also prove that the odd count is lesser than or equals to n minus 1, and so when you sum it up, so you can say that the total count is lesser than or equals to 2n minus 2, and which is strictly lesser than 2n, of course. Okay, so I leave that the odd part to you. Again, a very similar approach. Okay, so just try it out. Okay, and yeah, so we are done with this problem as well. Okay, so yeah, I think I'm done with all the problems. For problem 1 also, even like this part where I told you to show, so this is very simple, that just try to show that if you have any integer, that is let's take a is an integer, and if you take root over of a, then it's either an integer, it's either belongs to z, or it's irrational. Okay, so try to show this. So I think that will do the job of this. And problem 2 also, I think I gave you some part to prove. Okay, so I think I forgot, so no problem. So for every problem I gave you some part to solve, and also try to do them. And yeah, if you think that yes, I have made some mistake somewhere, or you didn't understand something, so yeah, please do let me know in the comments section below. And yes, so I'll also try to solve the others and post the solutions as soon as I solve them. Okay, so yeah, thanks for watching, and keep watching and keep learning. And yeah, that's it for this video. See you in the next one.